Hi. Let me turn down there. Good. And yes, of course, we are going to do some more. Um, oh, there we go. Of course, we are going to do some more. We're going to try and skip anything but three component systems. But as I look through the rest of it, um, of course, we haven't even looked at the refractive index part, which is something we're super interested in. So let's go ahead and pick up. Uh, Now, hopefully, we're going to pick up on 3.3 characterization of a selection of microemulsions. And we're going to do densities and see what trends there are in densities. So, density is an important physical property of microemulsions, but was also determined here as prerequisite input data for the measurement of viscosities using the automated AMVN viscometer. Viscosities that can provide further insight into some phase transitions possibly occurring. Okay, so yes, something that I know a little about is that there's a dynamic and a kinematic viscosity, and they're related by the density. So to move between them, yes, you have to know the density. Densities of the single components were measured first at 25 degrees Celsius for reference and found to be as follows: 0.997 for water, 0.95 for bridge 30, 0.887 with only 3 sig figs for both propyl acetate and ethyl propionate, and 0.786 for C3-ol. I can't remember if it's 1 propanol or 2 propanol, but anyway, figure 10 and figure S1 show the variation of measured densities of Windsor 4 microemulsions with the weight percent of the water component of the microemulsions for the pseudo-ternary system incorporating PRAC and those incorporating ETPR respectively. Both systems without co-surfactant C3-ol and those with, so where is, all right, sorry guys, sorry people, I gotta go find out, I can't remember. Co-surfactants, C3-ol, should tell me. And the propyl oh, they'll tell me in the materials and methods. Isopropanol, C3, yeah, that's what I thought. Isopropanol. We do things with 1 propanol as well. So back to where we were. Isopropanol were measured, R values shown being once again the volumetric ratios of H2O to isopropanol, ranging from 2 to 3 to 4. So let's go look at figure 10. Figure 10, variation of densities as a function of the weight percent of H2O incorporated for Windsor 4 microemulsion systems without and with different proportions. All right, so without, that's going to be a true ternary, and that one looks like it's this lowest one. So going to the actual document, figure 10 is blue. Oh, actually, this one is the one that we are interested in. And so let's see, it says density of microemulsion. So the ones without the isopropanol, yeah, okay, isopropanol is a lower density thing than water. It's the lowest density thing, I think. So 0.786, yes. So the isopropanol should, in general, lower it. So yeah, that makes sense. Connect that. So the density increases with more water, and yeah. Okay, the density increases with more water. I don't think that's surprising. Figure 10 and figure S1 show consistently a linear increase of densities with increasing water content, irrespective of the ester used as an oil component or of the proportion of isopropanol added. This suggests, on the one hand, that the concentration of the densest component, that is water, is a determinant for the overall density, and on the other hand, that a simple density measurement could be used to interpolate the water percent of the microemulsions based on the linear equations shown above. As expected, the more of the isopropanol was added as a co-solvent to replace part of the water, the smaller the densities obtained of the respective microemulsions as a result of the much smaller density of isopropanol. Good. Working with benzene, water, tween 20, and heptanol microemulsions, Mehta and Bala also observed that, irrespective of the relative composition, densities always remained greater than 1, dominated by their only component with a density exceeding 1, the tween 20 surfactant. All right, okay, so this is interesting. I love linear correlations. If you've taken Chem 400 at Sac City College, you have done this except with density of water, density of saline solutions lab. And so what they're saying is, if they measure the density of the microemulsion, they should, let's just say it's 0.97, and there's no isopropanol, they should be able to go using this equation right here over and down and be like, oh, it's 58% water in the microemulsion. Okay, that's interesting. Love that. Not sure how it's going to play out though. Down here, densities of the microemulsions were also estimated by using the following mixing rule: percent component of each component times its density, in which density calculated, percent, the results of the calculations are shown in supplementary tables S1 and S2 for Prac and Etper, respectively. From the data presented in these tables, it can be concluded that such estimated densities are fairly close to the real experimental values, showing deviations well below 5%. Okay, so that's in so the tables S1 and S2 are in the supplemental materials, and so we deal with non-ideal solutions typically for not not densities but refractive indices. And let's see, downloads. That's not where these are. These are in Chem 484. And I think I don't know if we have, we don't have okay, well, we don't have the supplemental, so we may have to do a separate one on that. Yay, refractive indices, 3.3.2. For the same selection of microemulsions, refractive indices were measured at 25 degrees, and the values obtained are plotted on figure 11 and figure S2, with and without a co-surfactant. Reference refractive indices for the single components were also recorded, blah, blah, blah. Okay, sorry, just looking. Water is the lowest. Bridge 30 is the highest. And we want, then these look like lovely XL ones. And without C3 is this curvy one, which has an X squared fit, which is different than all the other ones. So I'm interested to see where that comes in. Variation of refractive index, that is a fraction. Oh, now we've got H2O incorporated for Windsor 4 microemulsion systems without and with different proportions of added co-surfactant. R is the volumetric ratio. Okay, so wait a minute. So this says weight percent H2O. This says weight percent bridge 30. Uh-oh. Well, anyway, so is that doesn't make sense. And water percent makes sense for what we've been doing, but read on, as they say. For all pseudo-ternary systems, refractive indices increase linearly. Yes, those are all those ones. There was also an increasing trend, albeit not linear. Well, for the ternary systems lacking isopropanol, there was also an increasing trend, albeit not linear. The data suggests that the refractive indices of microemulsions are determined primarily by the component with the highest refractive index, for example, the bridge 30, and thus the experimentally determined refractive index could serve as a direct indicator of the concentration of this component on the basis of the curves above. Okay, this suggests that this is wrong and that is right, because it does say of the percent of the bridge 30 surfactant. I mean, it is interesting because you can do all of these plots because you have all the percents in an Excel file somewhere. So let's read this again. And thus the experimentally determined refractive index could serve as a direct indicator of the concentration of this component. Okay, for all of the systems with the isopropanol, but not, so there are, like if it's 1.37, not only is it very flat, which means you'd have to be very accurate, there are also two values for the bridge 30 that have the same refractive index. Okay, well, so yes, let's see if they say anything. The range of refractive indices obtained here, 1.36 and 1.43, is quite typical of microemulsions incorporating water, esters, non-ionic surfactants, and alcohol co-surfactants. Working with isopropyl palmitate as the oil, water, and a variety of tween surfactants, together with 1-butanol as the co-surfactant, Bashir et al. Obtained refractive indices ranging from 1.39 to 1.44. All refractive indices ones, RI star, are ones that we're probably going to want to look up. Hermansky McKay, let's stay on the screen there, showed that even when the oil was not an ester but an alkane, hexadecane, in combination with bridge 96 and 1-butanol, refractive indices remain similar between 1.34 and 1.44. All right. Well, hexadecane with bridge and 1-butanol. Okay, so now we're getting very close, okay, to a system that we're interested in. So hexadecane, so HD star, 1-butanol we've used. We have not used bridge 96, and so the bridges, so I use other ones so far, but so there, a couple stars there. We got lots of stars on this one, and these are references that we will have to look up and read in some context. Electrical conductivities. This seems actually interesting because I don't know. Electrical conductivity measurements, I think they might be not that expensive to do. So that's our interest. But have been used in past studies as experimental evidence for delineating the specific type of Windsor 4 microemulsion, water and oil and water, or bicontinuous. So where the bicontinuous, I'm guessing, is going to be the most conductive. This is because there's been shown that within, and the water ones will be conductive. Unless you're using pure water, let's see if they only do it for the salt. The conductivity of the water-oil microemulsions incorporating non-ionic surfactants increases. On the case of bicontinuous emulsions, it varies very little. And for oil and water systems, it decreases. Oh, okay. So with an increase in water content, the conductivity, so increase in water content. So, oh, it goes up, it stays the same, it goes down. So interesting. So I love a good trend. Trends in conductivity. Conductivity. But there we go. Can be evidence for type of microemulsion. Good. Well, we're going to be on this page anyway. Moreover, a sudden and pronounced increase of conductivity in the domain with low water content corresponding to water and oil microemulsions was shown to be indicative of a water percolation phase transition. Up to the water percentage corresponding to this sudden increase, inverse micelles are scattered in the oil matrix, but at the water percolation point, they approach each other enough to form clusters whose number increases from this point onward, and implicitly, there is an increase in electric conductivity. A further increase of water content leads to the appearance of bicontinuous domains, intertwined domains of water and oil. And then, when there is sufficient water, phase inversion occurs, and the microemulsion becomes oil and water, with oil-based normal micelles dispersed into water. Any additional water added past the phase inversion point leads only to the dilution of these micelles and thus a decrease in overall conductivity. That's actually, okay, so back here, I said increase in water contents, the conductivity of water and oil microemulsions incorporating non-ionic surfactants increases, and oil and water systems, it decreases. All right. So I think that makes sense because they're saying once you change to oil and water with any additional water added past the phase inversion point leads only to the dilution of these micelles, thus a decrease in overall conductivity. So, all right, there's again. Incorporating, so you add water, conductivity increases because the water is going into those water and oil micelles. All right, let's read this again. Okay. Okay. So, moreover, there we go, a sudden and pronounced increase of conductivity in the domain with low water content corresponding to water and oil microemulsions was shown to be indicative of a water percolation phase transition. So they're saying, I guess there's a slow but steady increase in conductivity for water and oil until you get to a water percolation phase transition, in which case there's a significant, sudden and pronounced increase of conductivity. And yes, it tells why, because they're clustering. They form clusters whose number increases from this point onward, and implicitly there is an increase in electric conductivity. Further increase of water content leads to the appearance of bicontinuous domains, at which point the conductivity stays the same. So let's see. So if I were to draw this as a graph, I would say increasing H2O, and that's going to be conductivity. I'm just going to write C there for conduct. Well, again, these are my notes. And I need to know what C is at a glance. So I'm going to write conductivity there. And these have no axes, but so you have this slow increase, and then a fast increase, and then essentially no change, and then decrease. And so this is 1, 2, 3, 4. 1 is water and oil microemulsion. 2 is water and oil microemulsion with percolation network. So we can, anyway, so they're still micelles, but they approach each other at the top with enough to form clusters whose number increases. And 3 is bicontinuous microemulsion. I hope I don't need this. Oh, yeah. That's the same graph. Okay, we try not to write on that again. And then this is oil and water. Okay, so this one here, whatever it is. All right, which one's the blue one? Without C3 all. This is figure 12. Yeah, this is the blue one. And this shows the behavior very nicely. So we would assume that here is 1, that here is 2. Well, at this point, we should read it. The curves, where do we leave off? The curves that depict the variation of conductivity for the same selection of microemulsions as a function of their water weight percent. Let's get all that on there. Good. Are shown in figure 12, PRAC, and figure S3 for ETPR, overlaid with their first order derivative curves. Oh, that's what they write. First order derivative curves are the blue ones. And so first order derivative. So, right. Change in slope is going to be there. Okay, that's interesting. Again, these are all Microsoft Excel. And interestingly, they have no hash marks here. It's our graphs will have hash marks. Oh, they have ones over here, though. Anyway, so let's see. We're only interested in the isopropanol-free one. So I'm looking at the ones with the actual colors, and they mostly, are they going to say there's no bicontinuous phase for some of these? Let's see. Derivative curves that reveal better local maxima corresponding to sudden conductivity changes at percentages of water where the percolation transition occurs in each system. All figures generally show the expected behavior with slight conductivity increases at first in the water-oil domain, then a sudden increase up to a maximum, followed usually by a decrease along the oil-water domain. The only exception is the system with water isopropanol R ratio of 4, figure 12. It's yellow. Yes, yellow. Yellow is this one that just keeps going up, where only the water percolation transition is observed, but not the decrease following the phase inversion, which is likely the result of a limited range of water percentages explored. From 0 up to only 80%. Overall, there is a shift towards lower water percentages of both percolation transition and phase inversion points as the isopropanol content increases, lower R values, which suggests that the alcohol co-surfactant facilitates the joining and then the merger of water molecules. Yeah, right. Again, not too worried about the part about the isopropanol part. Given the non-ionic nature of the surfactant, it comes as no surprise that conductivity values remain very low in all cases, from about 5 to 160 microsiemens per centimeter. Conductivity of microemulsions incorporating only non-ionic species is thought to be the outcome of statistical equilibrium fluctuations of micelle charges around a zero mean, where pairs of initially neutral neighboring micelles approach each other and undergo disproportionation, leading to oppositely charged micelles. Oh, this is very interesting. Two micelles goes to a positive and a negative one. So disproportionation, leading to oppositely charged micelles. Charged micelles. For microemulsions composed of non-ionic EL35, paloxyl 35, water, vitamin E, and ethyl butyrate as oil, and ethanol, phenol measured conductivities from about 10 to 160 microsiemens per centimeter, very similar to others. Working with microemulsions made of tween 20, water, benzene, and various alcohol co-surfactants, Meta and Bala, who we've seen before, also obtain similar conductivities. Conductivities, similar. Viscosities. All right, well, before we get to viscosities or whatever's next, let's go ahead and stop recording.